All right, so this is part 3 of our polar coordinates, polar graphs unit. We've talked about first just what were polar coordinates and converting between rectangular polar and plotting polar coordinates in the polar coordinate system. And then we looked at circles centered at the pole and lines. And then in part 2, we looked at circles that were not centered at the pole. They'd been shifted off of the pole, and lemniscates, okay, and how to determine the different type of lemniscate. You had the whole table to look at. So what we're going to talk about today is called a rose curve. In the Delta Math assignment y'all were doing, this is the one that was on the far left of the pictures. I said, if you get one like that, just skip it because we hadn't talked about it yet. So after our notes today, if you want to go back into that Delta Math, you could try some roses. For those of you who hadn't finished the Delta Math, you go in to finish it. You won't have to skip the roses anymore. You'll be able to do them. All right, so a rose curve, the function, the equation, the polar equation, looks like one of these. What is different about these equations than what we were looking at the past couple days? Okay, that in front of theta, that coefficient in front of theta. Okay, that is definitely different. We have not had a number, a coefficient on the theta inside the trig function before. That's how you're going to identify that it's a rose and not a circle. If that in was not there, this would be the equation of a circle, in a polar equation of a circle. R equals a sine of theta, or R equals a cosine of theta is a circle. So that in is crucial. That's how you're determining that it's a rose. Now, the a value is still important. We're still going to need to know what that a value is. If there is no number, what is a understood to be? A 1. Okay, so if there's no number here in front, a is 1. Okay, otherwise it's whatever is shown. Okay, so the a and the n are going to help us determine what our rose will look like. Okay, the a value is going to help us determine the length of the petals. Okay, it's called a rose curve because it has these shapes, these curves that look like petals on a flower. Okay, now how long each of those petals are is determined by a. Okay, so that is the length of the petal. Okay, that's a. Now the n value is going to help us determine the number of petals. Okay, but it's not as simple as, well, n is the number of petals. Okay, there's a little hitch to that. If n is an even integer, then there are 2n petals. Whatever n is, you have to double it if n is even, and that's how many petals there are. Okay, so if n is even, there are 2n petals. So in these two examples that are drawn out, this rose curve has 4 petals. So that means in the equation, the n must have been 2. This rose curve has 8 petals. So what would n have been for this equation? Good. Okay. And in both of these, the a value is 2 because those rose petals are 2 units long, right? Okay, so if you have to work backward from the graph, you need to be able to identify that stuff. Now, what if n is not even? You don't double. It is, if n is odd, that's how many petals there are. Okay, if n is odd, there are n petals. So in this example, there's 5 petals, so that means n must be 5. There are 3 petals, so n must be 3. Okay, what's the a in these two examples? Here the A is 3. And that one's also 3. So far, so good? So A and N, length of petal and number of petals. But that's not all we need to know. We also need to know the direction the petals should be drawn, okay? And that's going to be determined by sine or cosine, okay? Is it a cosine function or is it a sine function? Now, up until now, like when we were doing our circles and lemniscates, whether or not it was sine or cosine, what difference did that make? What did that tell us? Yeah, it told us it was horizontal or drawn horizontally or vertically from the pole. Okay, so we know that the x corresponds to cosine and the y corresponds to sine, right? Like when we did the unit circle and everything, and when we're drawing circles and lemniscates, if it was a sine function, it was drawn vertically. If it was cosine, it was drawn horizontally. Okay, so same idea here. If it is a cosine function, your first petal is going to be drawn at 0 degrees. Okay, so like this one here, see how there's a petal at 0 degrees? Okay, this must be a cosine function because it's got a petal at 0 degrees. Okay, does this one have a petal at 0 degrees? No. So this is not a cosine function. This one must be sine. Okay, this one has a petal drawn at 0 degrees. So this one is a cosine function. Now, if it's a sine function, it's not always drawn at the exact same angle. Like cosine is always at 0 degrees, the first petal. But sine is always 90 divided by n. Okay, so it'll vary based on the n value. So you can see we said these were not cosine, they must be sine. And notice n is 2, right? For this one, what's 90 divided by 2? So that first petal is at 45 degrees. Okay, in this one, n is 5. Okay, so 90 divided by 5, I know that's going to not be an integer, but that still tells you, or it is an integer, sorry, it's not a value from the unit circle that you know. It's not like one of the ones we have memorized or something, okay, but it's at 18 degrees. So this first petal here is at 18 degrees. You know, with me so far? Now, technically, this is also divided by n. 0 divided by anything is 0. So it's always 0 for cosine. Cosine always starts on the polar axis, which is 0 degrees. All right, now the rotation. How much space, how many degrees between each petal? Okay, how are they spaced? Well, they are always spaced evenly. They're evenly distributed. What's a full rotation around? Okay, so you take a full rotation, 360, divided by how many petals? The number of petals. And that's going to tell you the rotation between each petal. Okay, so you can see in these examples over here, there's 3 petals. 360 divided by 3 is 120. So there's 120 degrees between each petal. Y'all see that? Okay, this one here, there's 5 petals. What's 360 divided by 5? 72. So there's 72 degrees between each of these petals. Does that make sense? Okay, so that's how you figure out the spacing between the petals. Feel okay with that? All right, so let's try a couple of examples. We're given the equation and we want to graph the rose curve. Okay, so I'm going to first identify A, and that tells me what about my rose? the length. Good. So the petal length is 2. And then I'm going to identify in. What's that going to tell me? Okay, since in is 3 here, 3 is an odd number. What does that mean? There are 3 petals. Good. Okay, and then I'm going to look at what trig function it is. It's cosine. So that tells me that my first petal is where? At what angle? 0 degrees. Okay, and then I'm going to get the rotation between all the petals. So I'm going to do 360 divided by the number of petals, which we said was 3 up here. So there's 120 degrees between the petals. So far, so good? So now I'm going to sketch it. I'm going to say, okay, starting at the pole, I'm going out 0 degrees, 2 units. That's how long the first petal is. And the first petal's at 0 degrees. So 2 units out. So there's the tip of the first petal. Okay, how many degrees do I rotate to get to the next petal? So I'm going to go around. I'm going to stay at this, on this circle on the polar grid. I'm going to go 120 degrees around. That's going to be the tip of another petal. And I'm going to go 120 degrees more to 240. And that's going to be the tip of another petal. If I go 120 degrees, it gets me back to the first petal, right? Okay. Now, I can sketch this several different ways, but know that they are not, the petals are not pointed at the ends. Okay, so if this is how I was drawing it, just watch for a second. Okay, I'm not going to go like this and like put a point out here. I'm not going to do this. It's not pointed, right, and coming in together. That's not how it is. It is very curved, not pointed. Okay, now you can actually use your calculator to watch the path of the curve. Okay, you can actually, if you're plugging in angle measures from 0 to 360, you can see where the points should be. Like, which one of these points should I start at technically? Okay, so if I plug in 0 degrees, 0 times 3 is 0, cosine at 0 is 1, and 1 times 2 is 2, right? So I'm starting here at 0 degrees, 2 units out. This is my starting point, okay? And you can watch the path. I'll go over it again in a different color, but it curves through the pole down here, and this curves up through the pole to this petal, down through the pole back to the beginning. It's very curvy, loop-de-loop. Watch, I'm going to do it again in black. Okay. I'm going to show you in the calculator. Hopefully you watched the videos last week when I was out. When you were taking your notes, you were supposed to watch those videos because I went over some calculator instructions and setups, like the settings in the calculator to do polar equations. Okay, you can go back and watch those videos if you have not already. And I put a document in its learning as a reference sheet for the calculator with polar equations. Okay, so I'm going to show you this so you can see how that works. So when I go to y equals and I put in my polar equation, well, first of all, you need to know that you're in polar mode so that this shows as r equals instead of y equals. And when you click this button, it doesn't show up as an x, it shows up as a theta because it knows we're in polar mode. Okay, so when you go to mode, degree, and underneath that, polar. Okay, typically your calculator is in function mode, but we're doing polar equations. So degree in polar mode, and you can type in your equation. Now you want your window settings on your graph. Typically they'll be 0 to 360 for the degrees, okay, and then by 1. Okay, that means that the calculator is going to plot a point every 1 degree. Okay, so it's actually plotting 360 points to draw the curve. Okay, the larger this number, the more jaggedy looking the curve will be, the smaller this number, the smoother and rounder the curve will be because it'll have more points. Does that make sense? Okay. And then your X and Y minimums and maximums just need to be equal to each other. And 5 is fine for this curve because the petal is only 2 units long, right? So it'll definitely fit in this window, okay? If I go to graph it, oh, I have the wrong equation plugged in there. What was the equation? 2, 3 theta. Okay, now if I want to slow that down, I can go to the window and I can change this 1 to a smaller number. Watch if I make it bigger. Like if I have it go by every 10 degrees. Look how much more jaggedy that looks, right? Because it didn't plot as many points, it's not as smooth. But if I change it to less than 1, if I go to like tenths, I go to 0.1, it's going to have to plot a lot more. So it slows down and you can watch the path better. So it goes down, back up through the pole at the 120-degree angle, back through the pole to the 0. Does that make sense? Okay. Now the reason it's going in that path is because as you rotate, you can go to your table and see. Okay. At 0 degrees, it was at 2. That was that first point we plotted. If you plug in a 15 degrees, this is what it comes out to, a 30 degree. And you can see the actual points. And if you were to plot all those, that's the path that it follows. Does that make sense? Okay, so you can use your calculator to check your graph or to view like the path for drawing it, if you prefer to follow the correct path. That's a good tool to use, okay? Now, if you want to make your petals more accurate in like their width, okay, because my drawings, my sketches this is not perfect. You see how I have this space in the middle? I didn't actually cross exactly through the pole. My graph is not perfect. This petal looks bigger than this one. Like, it's okay. It doesn't have to be perfect. But we are going to be doing a project for our test grade on Unit 5. And on that, I would like your graphs to be accurate and not just quick little sketches like this that aren't perfect. You know, it's never going to be perfect, but more accurate. So on this one, I only plotted the 3 points, right? I just did the tips of the petals and then I sketched it. When you're doing the project later, I will ask you to plot more points and get the width of the petals correct, okay? So maybe like a point or 2 points on each side of the petal to make sure you're getting them the right width and it gets them more equal as well, okay? All right, so let's look at the second example. We've got an A value of 3, which that's going to be the length of the petal. We've got an N value of 2. What does that tell me? That's an even number. So what does that mean? So there will be 4 petals. Good. You got to double it when it's even. This one is a sine function. So my first petal will not be at 0. It'll be at 90 divided by N, which is 2. So it'll be at 45 degrees. N is 2. It's always 90. That's what we wrote here. It's always 90 divided by N. If it's a sine function, you always do 90 divided by N to see where the first petal should be. Okay, so make sure you have that written down there to refer back to. Okay, so 90 divided by N, which was 2, is 45 degrees. So the first petal is going to be at 45 degrees. Now, the rotation, the spacing between the petals, it's 360 divided by the number of petals, which there are 4. So the spacing is going to be 90 degrees between each petal. but we start at 45. So I'm going to start at 45 degrees, 3 units out. So that's going to be the tip of the first petal. Then I'm going to rotate 90 degrees. So that's going to put me at 135. If I rotate another 90, that's going to be 225. And then another 90 is going to be at 315, right? So those are the tips of the 4 petals. Okay, so again, you can look at this in the calculator to see the path that it's drawn. So what is that? 3 sine 2 theta. Okay, so you can see it starts at the pole and goes out into quadrant 1, loops down into quadrant 4. Going to come back to the pole and go to quadrant 3 because it just keeps that, it keeps on swirling around nice and smooth. You all good with that? I'm going to sketch it in that order now. So I'm going to say, okay, go up into quadrant 1, down to 4, 3, and 2. Feel okay about roses? Okay, now again, if you wanted more points to make sure the width of your petals were correct, I'm going to show you again in the calculator real fast. You could go to your table and you could see, well, at 30 and 60 degrees, like the tip of the petal's at 45, right? But at 30 and 60 on both sides of it, it's around 2.5, right? So I could have put at the 30 and 60, I could have gone 2.5. Oh, I did that pretty good. 2.5. It should have been up here, you know, a little bit more. Okay. And if you wanted even more than that, you could say at the 15 and the 75, it should have been at 1.5. So I could say at 15, it should have been at 1.5. 75, it should have been at 1.5. So I should have made my petal a little bit wider, right? Okay, but that's all right. When I do the project, I'll be a little more accurate. Okay. You'll feel good with roses? All right. Last shape today is what's called a lemniscate. And I know that doesn't look like that's how it's pronounced. Lemniscate. Okay, kind of like limousin was pronounced different than it looked. They're French. All right, so what is different about these equations? How do you think we'll identify those as lemniscates? I think somebody started to say it. The R is squared, right? That's different. All the other equations are R equals. This is R squared equals. Okay, so we're going to know it's a lemniscate because it's going to be R squared. Yeah. And lemniscates will always have 2 pi, or not, excuse me, theta, 2 theta in the trig function. Okay, but it's not a rose. It's similar to a rose, but it's not a rose because of that squared. Okay, so it's not like the rose where we're going to double to get 4 petals. Okay, this is different. We're going to write down the rules about it so you understand. Okay, A is still the length of the petal. There's still petals, and A is still the length of the petal. I'm going to come back and put them on the graph here in a second, but I just want to jot this stuff down. Okay, but there are always only 2 petals in a lemniscate. If there are only 2 petals, what shape does that make? A figure 8. Good. Because if they are evenly spread out, they're 180 degrees apart from each other, that just makes a figure 8 shape for your 2 petals. I think I just said this, 180 degrees apart. That's the rotation is always 180 degrees between the 2 petals. Now, if it is a sine function, it is always drawn at a 45-degree angle. Because remember, didn't we always say 90 divided by n? If the n is always 2, then it's always going to be at 45 degrees, right? And cosine will always be drawn at 0 degrees, okay? So I'm going to go back and sketch an example on these two. If it's helpful to you, you can sketch like a line or a dotted or dashed line at the angle that you're drawing the lemniscate, but you don't have to. Now, we don't have specific numbers on these, so I don't know how long the petals are supposed to be. So for the sake of these examples, I'm just going to go to 3. Okay, so it's just this figure 8 shape at a 45-degree angle or at a 0-degree angle. Just 2 petals, 180 degrees apart, figure 8. Now, you need to be careful about your A. A is the length of the petal. In your equation, you have A squared. So this number that you see in front of sine or cosine is squared. So how do you get A? You're going to take the square root of whatever that number is, right? Okay, so that's what we have to be careful with on these examples. Okay, we have R squared, so we know it's a lemniscate. A squared is 16. So what is A? A is 4. So the length of the petal is going to be 4, and this is sine. So it's going to be at a 45-degree angle. One, two, three, 4. 4. Now, if you wanted to plug this in and get a better width of the petals, you could. I don't know if I'm drawing them as wide as they should be. We can check it. 16 sine 2 theta. Now, to put this in the calculator, I can't change R equals to R squared equals. So how would I solve for R? How would I get rid of that squared? I would take the square root. So plugging it into the calculator, I'd have to type this in as the square root of 16 sine of 2 theta, right? Okay, so that's how I have to plug it into the calculator. And when I graph that, I'm going to see that lemniscate at the 45-degree angle. Now, that is much wider than I drew it, right? Okay, so I probably should have drawn mine wider. Okay, so I'm going to go to the table and see. Okay, so at 45 degrees, it was out at 4. So at 30 and 60, it was at like 3.7. So let's see, at 3, should have been a little up higher there, 3.7, right? And then at 15 and 75 is at 2.8. So that's not terrible. It should have been 2.8, yeah. So mine should have been just a little bit wider there, right? Y'all see that? Okay. All right, but you get the idea. That's a lemniscate. Now this one, A squared is 4. So what's A? And it's a cosine function, or cosine is the trig function there. So it's going to be along the 0 degree, just out 2 units. I know I didn't draw that perfect. I definitely drew my curves up bigger above the x-axis than I did below, but I think y'all get the idea. You can always go in the calculator and get those additional points and plot more to make it more accurate. And that's what I will expect you to do on the project, not necessarily the homework though. Okay? Any questions about roses or lemniscates? Okay, so I'm going to pass out the this practice worksheet. It's just one-sided. It won't take too terribly long, and it will be due on Thursday.